Okay, so I'm just going to wait just a minute to let people join, and then we'll get started. All right. So hello, everyone. I'm Renee Yager, and welcome to today's webinar, Design with GaN Power Electronics for Smaller, More Efficient USPD 3.1 Fast Chargers. Before we get started, I would just like to go over a few housekeeping items for today's events. You can submit text questions to the panel by typing your questions into the Q&A feature that you can see at the bottom of the screen. You may send in your questions at any time, and we will collect these and address them at the end of today's presentation. Now, I would like to introduce our speakers today. Josh Fang is Senior Director of Strategic Product Marketing at EPC. Josh has over 16 years of experience in the power electronics industry and in product management and applications engineering. Also on our panel today is Brian Miller. Brian is our Field Applications Engineer for the Americas. He has over 30 years of experience in power electronics as a design engineer and as a field applications engineer. Brian and Josh, thanks for joining us today. And Josh, you can take it away.
All right, thanks Renee for the introductions, and good to see many audience over here. And let's get it going. So today we're going to talk about USB PD, and we spend the next 40 to 45 minutes talking about some of the market trends. Actually, let me present the agenda we're going to go over today. Some of the PD, Type C especially, market overview, the challenges that we've been seeing, and some of the challenges that customer has expressing along the way, and what are the solutions for those challenges. And we're gonna wrap it out with what kind of EPC have to offer in this type of portfolio, or what our portfolio that can solve those challenges is. And last but not the least, we finish out with a summary. Okay, good. And let me share with you guys a very simple quick question, slides. Remember this, I happen to have one of my outlets still kind of look like this because my significant others believe that every single electronic device require a dedicated power adapters. You know what? That's not quite the case anymore, right? I think many of the audience are aware, many of you has using Type C to charge your phone, to charge your laptop, to charge your monitors, etc. And that really the implementation of USB socket is really changing for the really fast in the last 2 to 3 years. As a quick definition, Type C plus PD will really simplify our life. You're unifying all the cable types to hopefully just one type, and bidirectional transmit and receive data as well as power. This is great, right? And to kind of share with you kind of the Type C and PD, really the Type C cables really can transmit both power and data. As you probably know, Type C port can source and sync power as well as transmit and receive data. Per actually the latest European charger mandates, that all devices sold in Europe need to have a USB, need to use Type C by 2026. That's coming up in just 3 years. As a consumer, it's a huge benefit because imagine in the futures, by in 3 more years, you just have to have one cable that can potentially use for all your power electronic consumer power electronics device, or even some industrial applications. PD 3.0, the lower voltage, lower current version, has been getting quite a bit of traction already. You might see some of the adapter advertising 60 watts, 100 watts. No, those are typically the 3.0 the protocols. Now the 3.1 are starting to take over place and deploy in 2022. Among all the chart, I'm not gonna, since we focus a little bit on the power sides, we're not gonna touch base too much on the data perspective. In terms of focusing on power, you typically have the sourcing parts, which is typically commonly known as adapter or car charger. And the middle sessions, you have the DRP dual rule power device. Typically, those are the device has some of battery that you can both syncing and sourcing powers. And there's a couple of different sockets out there. For example, a charger device. You have on the secondary side, you have SRs or multi-port buck converter. On the primary side, you can have a PFC plus ACF topologies, or totem port plus some of the newer asynchronous half-bridge topology That's typically more addressed by high voltage GaN device than these days. On the DRP session, dual rule power, we're seeing some of the socket, for example, buck converter and buck boost converter are starting getting more popular. Now, the question is, okay, great, 3.0 is good. What's next for PD? And this is setting us, using as a refresher for this audience who are not familiar with the PD. And PD, the next move is actually the PD 3.1. And the current will be increasing from a conventional 2 to 3 amps to 5 amps. The voltage side will increase to 28 volts. That's the first step. I've been seeing some of the upload products. I've been advertising 28 volts. And in the future, it can go up to 36 volt or 48 volts, meaning that the max output power, if you multiply voltage and current, that would give you a maximum of 240 watts. That's quite a bit of power to address many of the consumer products out there, including some of the gaming laptop, for instance. And we are as a GaN solution company, we are the enabler to enable those consumer power electronics products. But at the end of the day, we're seeing some of the new products out there the last years, for example, mentioning, hey, we have a PD 3.1 fast charging that within 30 minutes can charge your MacBook 56%, more than 50% of your battery lifetimes. And or some have a marketing claim that can charge 3 times faster than the conventional chargers, which is great actually great for consumer users. You might also argue that, oh well, do you really need such a fast charging for a laptop? Let me share my experience. Maybe I was more of a kind of a disbeliever when there's a fast charging coming out for a smartphone. But really, once you're able to charge your phone 5 to 10 minutes, you can get about 50% of run rate of your smartphone device. That's awesome. It's quite difficult to go back to a slow chargers. And I believe laptop or some more power hungry consumer electronic device will probably see that trend in the near future as well. Then the next, in terms of market overview, the question is there enough market for this PD 3.1? And as a matter of fact, let me just kind of share with you kind of the overall market size. This is not addressing particular semiconductor device, it's more addressing the system units. It's all combined just on the kind of sourcing device. If you're just talking about charger, for example, tablet charger in a box, smartphone charger that come in the box that ship together with a smartphone, or some aftermarket charger together with a notebook charger, they all exceed, the total combined exceed more than 1 billion system units a year. There are some moving trends. You probably noticed some of the smartphone nowadays, for example, take iPhone as an example, or some of the Android phone, they don't ship with the inbox charger anymore. So that trend is, that will kind of have a very likelihood to reduce the overall charger units. However, the number of Type-C ports output will likely to stay the same or higher over time, because some of the aftermarket and notebook charger, you will probably seeing, instead of the traditional 1-port Type-C or USB, you're seeing some more of 2 ports or 3 ports coming out in the market. And on the kind of on the DRP products perspective, for example, desktop, tablet, notebook, power bank, smartphone that continue to grow, especially after the pandemic. This is also good moving trends for the entire, for example, of a buck converter or buck boost converters. Now, I want to spend a little more time on the kind of the challenges that are being seen, right? And then there are 3 challenges. We identify kind of 3 challenges. I will go through kind of one at a time with you guys. The first one is kind of the AC adapter sides. AC adapter side, as you probably know, the primary side are typically nowadays are addressed by high voltage GaN device. Here, I want maybe touch base a little bit on the secondary side, especially this multi-port Type-C sockets. As you know, in a charger or adapter, the cooling, there's not much air cooling. The cooling method is quite minimal. Best case, you cool from PCB. There's no air convections. PCB space is also quite limited too. And if you look at very carefully on those output ports, the inductor does take in each individual ports, the inductor does take about half the height. If there's a way to really hopefully minimize it, you can potentially put more ports in adapters, a charger or adapters. And the last but not the least in this type of challenges, for today, up to 100 watts or 20 volt output 5 amps, you can potentially use a 30 volt silicon MOSFET transistor or integrated silicon MOSFET transistor to provide that bucking from, like say, 20 volt to 5 volts or 28 to 5 volts. But as the PD 3.1 voltage are increasing to 28, even in the future 48, your 30 volt silicon MOSFET will no longer have enough design margin to do the step down conversions. As you will need higher voltage transistor in order to provide step down conversion. And typically, as you go up voltage, your figure of merit will diminish as voltage increase. The second challenge we're seeing is more of the kind of on the DRP side, and I would take a DRP product, for example, a premium or gaming laptop. Typically, in those type of products, unlike more of a consumer level laptops, 65 watts probably enough. But for premium or gaming laptop, typically they require 100, 120, 150, or 250 watts, or some gaming laptop require up to 300 watts power supplies. So, and those cable I was at CES shows just this year. I've seen many really cool gaming laptop. But one thing that have in common, they have pretty thick cables. Those cable are not a standard 5 amp cable, I believe. They typically, for example, take a 250 watts examples. 20 volt output, you will need 12 amp. Those are probably most likely specialized cables, and that will run higher cost and bigger power supply brick. So PD 3.1 could be a very, very attractive solutions because it can provide up to 48 volts and 5 amp, which basically is already 240 watts, and they can run much thinner cables. However, you still need, because most of the laptop this day is running out 12 volt, 19 or 20 volts input. So you still need a one additional DC-DC stage to convert your higher voltage PD to the required voltage on the notebook battery size. And that takes space. No, it's not exactly free. So additional high power density conversions is required there. And furthermore, if the input voltage increase in the future to 28, it's already happened. 28 volts already happening. If in the down futures, near future for 48 volts, again, your higher breakdown voltage MOSFET device definitely need more than 30 volts. And when you go above 30 volts, 30 volt has actually 30 volt, 20 volt device has a pretty good figure of merit for fast switching megahertz. But as you go above that, 40, 80, hundreds, higher switching frequency can really be a bottleneck, especially in a higher density designs. Now, to address one more challenge before I kind of go down to the solutions is, again, as we're seeing, the PD voltage are increasing. So in the typically DRP products, for example, if you're running a 12 volt batteries, in the past, you just have to down convert to 5 volts. But that no longer the case. Conventional step down converter is not sufficient anymore because PD need to address quite a wide range of voltage, right? You down 5 volt all the way in the future, 28, 36, 48 volts. Even a simple buck boost converter doesn't quite offer the efficiency that's quite enough. Therefore, that we're seeing some kind of force switch buck boost converters in the market, whether with the mostly with the MOSFET today. However, there's also a little bottlenecks there because the MOSFET switching frequency, switching speed is quite limited. And as you want to go higher power density, shrinking the inductors, you do need to go above, for example, much higher frequency speeds. and the loss of standard conventional MOSFET become more contribute much higher than potential next disruptive GaN solutions. Okay, now if I to go back to the first challenges, which is the AC adapter on multiple output buck. Typically, at this case, I take a 5V as examples. If we were to address this with a kind of a GaN, mid-voltage GaN solutions, you can potentially deliver a very high density DC-DC buck. Maybe, for example, I take our EPC 9160 demo board as example. This is running at 2 megahertz switching with our 40-volt 2055 device paired with ADI 7890 gate drivers. And if you simply look at it, right, and this is obviously a two-phase design, but you can also convert it to one phase. It's just the conversion portion is about 2 centimeter by 2 centimeters. That will give you two phase, and they can do obviously much higher current than PD. In the right hand side, kind of highlight the most likely PD operating area. Typically, is up to 5 amps. In this case, you're able to get a good 93% efficiency out of, for example, 24-volt or higher voltage to 5-volt output. And the power loss is about 2 watt or less. If you think maybe, and if you want to, for example, improve efficiency further, you can potentially reduce the switching frequencies to further improve the efficiencies. But I think right here, I want to kind of highlight one thing is the inductors, you can definitely shrink quite a bit. I mean, those are, you can actually typically standard come with a 2.2 microfarad sound switching, high switching frequency, 1 megahertz or 800 megahertz, you can run 1 microfarad. In this case, when you switch at 2 megahertz, you can go down to like 0.47 microfarad. What does that mean? That means your output PD type C ports can really be minimized. Ideally put more ports at the AC/DC charger, for example. To address kind of the challenge number 2, which is talking about some of the DRP products out there. For example, I take a notebook example, premium or gaming notebook. In order to be compatible to the future PD, you do need kind of a one stage conversion, and which is definitely need more than a 30-volt device. And I'm taking our generation 5 to run this performance as example. This performance is actually quite promising already. If I take 48-volt inputs, let's assume that 48-volt from PD, and the output is 12 volts, switching on 1 megahertz. Our 2 Gen 2 products can run about 95% efficiency at the full load. In this case, you might ask, oh, how come why not 20 amps? In this particular case, we kind of limit our case temperature to 110 degrees and absolutely no heatsink, 0 heatsink, and about 1000 LFM. And depends on the product that you were to choose. 2204, it has a little bit higher RDS, better switching parameters. Therefore, the light load to mid load performance is better than 2218. 2218, however, has a lower RDS, and therefore the performance was shifting toward heavier load performance is better than 2204. And by the way, all those losses calculations, actually, there's all those losses bench tests include FETs, inductor, and other components. The device is actually generation 5 is quite promising already. However, if you were to take one more step forwards, our generation 6 device is literally second to none. And maybe I was starting from this. It's definitely more efficient than our Gen 5, and it could be half size of the 2218. Enable a couple more amps extra current with the same footprints. Reduce requirement of heatsink, optimize efficiency for all range. From light low, if you look at our frequency sweep, current sweep from light low to all the way to 20 amps. Our generation 6 in this particular case, the part number is EPC 2618, can even outperform our own generation 5 all the way to 20 or 22 amps. It provides two times the higher current density as well as at the light load, 2 times lower switching losses versus the 2218. So this is actually very promising. I think this is kind of the key reasons that EPC, as a very innovative GaN company, will continue to improve ourselves generation over generations. In this case, we definitely are able to outperform our generation 5. And this particular product, 2619, is quite suitable for our future high power density, high switching frequency PD applications. Now you might also ask, well, you're kind of comparing to yourself, right? What about you compare to some of the best in class, some of the better MOSFETs, silicon MOSFET solutions out there? How would you compare? And I've been hearing from customers this particular product, for example, from Semi, it's 80-volt device compared to our 2619. 2619, despite 2619 is 1.5 times higher RDS(on). Our QG, QGD, QRR is definitely a magnitude better, and size-wise, it's 2.4 times smaller. Then you might ask, hey, Josh, you are not really comparing apples to apples. You are comparing, you should use maybe a similar RDS(on) device to silicon as more fair comparison. Well, yes and no. I mean, at the end of the day, what is our designer, if it's a PD solutions or any other solution, what is our customer actually cares? We care about RDS(on), yes, but however, no, in a sense, at the end of the day, it's the thermal, the efficiency, the power loss that's really the outcome that determine the outcome of selections. So in this quite interesting one, right, you might think the performance might be not as good as a low RDS(on) device, but quite the contrary. 2619, I will show the more of a performance bench test later. As a quick takeaway, actually, even though the RDS(on) is higher than 80 volt, another 80 volt device, a MOSFET device, it provides 2%, as high as 2% higher efficiency, and with the same switching frequency at 500 kilohertz. And this is with the same inductor, 2.2 microfarad. However, even the size smaller, it actually stay cooler, 15-degree cooler than an 80 volt silicon device. And on top of that, the max current can even push 3 ampere more. Last but not least, because as much better figure of merits, 2619 is even able to switch at double the switching frequency, in this case, 1 megahertz, and use half of the inductors, 1 microfarad, to further reduce the space. And the efficiency, by the way, is still at least 1% better than silicon at 500 kilohertz. And just kind of just share to summarize what, to recap what I shared earlier. In this particular case, if you look at the orange line, is the silicon 80 volt device efficiency. Typically take a 48 volt input, 12 volt output PD is upward by 20 amps top. In this case, if you compare a 2619, exactly the same switching frequency, exactly the same inductors, at the top, it can provide 2% high efficiency at mid load, about 1.5% efficiency at heavy load. And if you were to benefit from higher switching frequency or using smaller inductors, even like, for example, 1 megahertz in this case, the green line is still at least 1% better than 80 volt silicon device out there. And this is obviously running at 400 LFM. If you were to able to have the possibility to increase to 1,000 LFM, the output current can push a little bit further. So I think one key takeaway, this is the type of kind of breakthrough that makes the future of GaN device so attractive. And I'm really looking forward to some of the future PD implementation, taking a huge advantage of our upcoming 80 volt device or 100 volt generation 5 device. Last solution to the number 3 challenge was kind of debugging or typically conventional USB is always 5 volt, 12 volts, or 12 volts. But in the future, what's happening is you're seeing some 20 volt or 28 volts coming up in the future, 36, 48 volts. a conventional kind of buck or conventional buck boost is not sufficient anymore. What we're seeing is some more of a 4-switch buck boost topologies that's being released in the market. And we have been kind of working with I would take one success story from one of the IC controller company that they were able to actually reduce more than 50% of the footprints. In this particular case, it's a rich type controller, buck boost controllers designed for power bank, docking stations, for instance. And what they have, their very original design is the inductor is about 4.7 microhenry and with a QFN package MOSFET. And if you look at the original kind of evaluation board reference designs, that big chunk itself, it take half of the space. Even you have a pretty small controllers, but all the output stage, it's quite significant in terms of space, taking huge space from this great product. So after a couple elaborations with them, the latest revision of the eval board, they were able to really reduce, taking advantage of a 100-volt GaN device, they were able to reduce the kind of buck boost session of the footprints by about 50%, more than 50% actually, and efficiency increased up to, they claim that improve 1 to 2% efficiency. And in this case, they believe the further space optimization can be achieved in the final designs. And this is actually quite attractive. Think about, if you're using as a power bank or mobile charging stations. I mean, for those power banks space, it's very space limited. Shrinking space by half is really, really good for the overall industrial designs. And here I want to share with you just kind of a couple of charts that we put together. Why there's 5-volt output, 9-volt, 12-volt, all the way to 20-volt outputs with a different input voltage. The efficiency at more of a key efficiency or 1 to 5 amps. It's about they're all above 90%. Of lower at the switch lower duty cycle at 5-volt, for example, is 91, 92%. As you go up to a higher voltage, they claim that they can switch efficiency can improve up to about 98%. Overall, compared to a silicon MOSFET solution implementation, in addition to all the space savings, the overall efficiency can be improved by 1 or 2% on top of all the space saving. This is awesome. Now, after all the solution and challenge that we discussed, I think maybe I'll spend another, let's see how much time we have, maybe another 10, 15 minutes, just touch base on what EPC have to offer. So our audience here have ideas, what are the solutions that they can maybe take advantage from. Here I want to kind of show a quick lineup of our Generation 5 products. And among all of those, we have basically the 40 volts solutions and 100-volt solution all the way to 350-volt solution. And that's in terms of PD, I think they're a little more applicable. For example, if it's 20-volt or 28-volt outputs, the 40-volt family will probably more suitable in terms of performance as well as from pricing perspective. If you need to go up to 36-volt or 48 volts, the Generation 5 100-volt device, maybe in this type of category, less than 10 milliohm device will be something a little more attractive. In terms of if you have to implement some type of synchronous rectification, which we didn't touch too much here, the popular choice will probably be, for example, 150 volts, 170-volt device or up. And I think if there's any audience out here that might ask, oh, what about you didn't talk about your Gen 6? I think Gen 6 is quite important that we mentioned earlier from one of the solutions. And I think it's important to kind of dedicate one slide just to talk, just kind of briefly highlighted our Generation 6, which the product is called 26819. We did a press release, early engineering press release back in November 15. We got a lot of good tractions and a lot of good inquiries. So I think this particular device is 80 volt, 3.3 milliohm RDS(on), very well suitable for type of future PD, whether 36 volt or 40 volt applications. If you haven't had a chance to take a look at it, definitely check it out. Then here, the last two slides, I've been talking quite a bit on the CSP, BGA packages. What about, if you have some type of industrial PD application where your contract manufacturing or your EMS are not quite familiar with ESP, CSP, or is there any other kind of QFN options out there? As a matter of fact, yes, yeah, we do have start sampling. We released one device called 2302. 100 volt 1.4 million device, and we'll start sampling all other 100 volt, 150 volt, 200 volt family in terms of a more of a completely footprint compatible 3x5 QFN packages. So if any reason you desire a lower voltage device, and for any reason you need to swap a higher voltage, or you can basically just replace, you can desolder the device and put a new higher voltage device. You might have to adjust, if you have some current sensing, you might have to adjust some current sensing limit. But otherwise, in terms of footprint compatibility, this is something we're trying to target and hopefully to benefit our customers to have very scalable platforms for in terms of QFN implementations. And each of the SKU 100 volt, 150, 200 volt, they come with a full size, the lower the RDS(on), and the other one come with a half size, have the RDS(on). So customer have the option to choose whether they want the best performance or they want some type of balance between pricing, a better price versus performance. Now, we talk about CSP, we talk about QFN. Some customers ask, what about, do you have any of the, to enable even higher switching frequency or make it easier layout? Do you have power stage? Yes, we do we have samples available out there. We call the 2310X family, 102, 103, 104. Basically, again, like the previous QFN portfolio, they are 100% footprint compatible. Today we're releasing 100 volts. They come with the different flavors, 6 million all the way to 10 million, addressing different output loadings. And the kind of the target applications that this particular product is focusing on the buck boost converter, block converter, or boost converter, motor drive, as well as a Class D audio amplifier. Essentially, what's inside is basically a gate driver together with a two integrated GaN device all in one package in a about 3.5 by 5 millimeters package. So in terms of, if you don't have to worry too much about all the entire external layouts. This definitely is higher switching frequency, a little more friendly. And here I want to kind of share you our experiment result of, for example, taking a 28 volt input from a PD, down convert to a 12 volt, for example, in a notebook in this particular case. On the left-hand side, you can see at 1.8 megahertz switchings. You can, let me see, okay, 5 amp, this is the input current at 5 amp, typically max input current from PD is 5 amps. They can generate about 140 watts. Yeah, even half the load, you can easily achieve 96% efficiencies. Or a good 5 watts or less power losses. And if you plan to kind of, again, further improve the efficiency, you can reduce the switching frequency a little bit. In this particular case, we try 1.2 megahertz as well. It can further improve. If you go down to 1 megahertz, you can further improve, or probably say efficiency improvement from 0.2% to 0.4% improvements. If higher switching frequency is not quite the end goal there. So in this particular case, the device under test is called 23104. Offers a very compact power stage and simplify customers' design, especially high switching frequency and high density design. I think last but not the least, we also have, in the case if customers are designing for industrial or more of a automotive level, automotive qual PD applications, we also have a line of Q101 GaN device available out there. Total today we have released about 11 automotive qual GaN device in productions. We probably have the most comprehensive mid voltage AEC GaN in the industries. The three most recent release product are our generation 5 products, 80 volt, so-called 2252, 2204A, 2218A. If you had probably the sweet spot will probably be 36 volt, 28, 36 volt, or 48 volt output PD in your car in the future. Obviously, we're not kind of doing this alone. We also have a portfolio of working with many gate driver controller company to create this whole mid-voltage GaN ecosystems. And here kind of list our product that we suggested to be compatible to our GaN device. Obviously, the list is the one I've been working with. I'm sure the available devices out there are much bigger than this. But so far, this is the one we have been used in the past, or vice versa. The control company has been using our GaN device in their own customer and been successfully implement and helping their customer to accomplish the for productions. All right, that's my last slide, and I will just kind of run quickly on the summaries. Number one, PD 3.1 is demanding higher current as well as higher voltage, as you probably seen, I mentioned a couple of times. Higher power density and small form factor design really require a paradigm shift in technologies. And I think GaN could be a vehicle to get us there. EPC has the widest GaN solutions offering, especially in the 40 volt to 350 volt space. As you're probably seeing, our products quite differentiate, and we perceive ourselves as an innovative company, continue to re-innovate ourselves. Product differentiation, integrating with the IC is also a part of a next roadmap. Partnership with a different controller, gate driver company. We believe all those are key ingredients to empower the future trend of high voltage USB PD. And I'm looking forward to working with many of you guys out there to really enable these ecosystems. And of course, last but not least, reach out to our technical expert if you'd like to learn more about our solutions. And here I create a little cheat sheet for the audience here. We'll share the slides in PDF file later on. If you want to get more email, direct contact to our technical field team, check us out at our Ask GaN Expert site. If you're more like a forum type of searching type of guides, we also have a tech forum that highlight many questions that customer ask. We also address those questions one at a time. Last but not least, what about if you just have a silicon device that you are looking for more of a GaN replacement? Check us out on the cross-reference page that can, if you enter a part number, for example, 80 volt, 100 volt, silicon device, it will populate a list of recommended GaN device that we think could be suitable for your applications. Okay, that was my last slide.
Okay, thank you, Josh.
Thank you. Yeah.
All right, so now we're going to start answering questions that have been submitted during the presentation. As a reminder, you can still go ahead and submit questions by typing them into the Q&A feature that you see at the bottom of your screen. So our first question is, if efficiency is my primary design requirement, what is the best GaN device for a load ranging from 250 milliamps to 5 amps at, say, 25 volts? Or is this more indicative of proper inductor selection and board artwork?
I guess I could take that one. Yeah, that's a common question. Like a given set of circumstances, what is the best GaN FET? A lot of times, because they're so small and so forth, it seems a little bit different. EPC has oh, I'm sorry, go ahead. Oh, okay. EPC has a very nice tool online. Am I allowed to share my screen? I'm not sure if I'm allowed to do that.
Yeah, go ahead.
Okay.
Let me see if I can share mine.
Okay.
Stop sharing. Okay, you can take over.
Okay, let's see. Here we go. Share. Right on our website, there's a nice little tool here. I hope you can see this. No, yeah. There we go. Okay. the GaN selection tool for buck converters can also be used for boost by going backwards, but nice little feature here is you can add an already preloaded 5 amps output, 25 volts output. I think that's what you meant, 48 volt input. And it goes down here and it ranks the FETs in order of power efficiency. So you can see which ones, trade-off of size and so forth, that type of thing. And that's for the top FET. And there's a little hidden box here. You type there, and it loads the bottom FET. So you can see the little ones here. And you can also, there's a little thing inductor here. The inductor current is shown. You can change the inductance and see what happens if you lower the inductance, keep on going down inductor size. In many cases, the efficiency actually increases. So that's probably the best answer for this. Look at this, find some parts that are listed as preferred, and or a few to look at in further detail. As far as board design, we have many example board designs that you can copy or look at, and that'll help preserve the good efficiency also.
Thank you, Brian.
Thanks, Brian.
What is the expected date for Gen 6, the 2619, and it's for the 90153 deliveries to begin?
Yeah, so the Gen 6, I believe it's going to be in terms of release toward the end of this year. Right.
Yeah, so you said
so
you're beta sampling now, right? So
yes, that's right. We're beta sampling right now. The production will happen toward the end of the year, and so as the evaluation boards.
Okay. Another question: if GaN is used on the secondary side of an LLC center tap configuration before the synchronous rectifier IC can give a gate signal, what is the state of the GaN?
What is this? That's a good question.
What's the state
Brian,
of GaN? I guess I would think it'd be off if there's no signal coming in. Is that, it's almost like a trick question. What's the question again? Maybe you could read it.
It says if GaN is used on the secondary side of the LLC center tapped configuration before the synchronous rectifier IC can give a gate signal, what is the state of GaN?
I'm not sure I understand then. I'm sorry.
Yeah, I don't quite get it. Maybe we can take this one offline a little bit. We can get back to the
okay. Somebody else is saying, because usually if you're using a MOSFET, the body diode would conduct.
Oh, okay. Yeah, GaN FETs have diode function too, so it works very well in those situations. There's kind of a perception you don't have the diode function in GaN FETs. You do. You don't have a parasitic element with the bad characteristics like in a MOSFET parasitic diode, but GaN FETs do have an excellent, very fast diode function. So yes, that'll work very well.
So you talked about using very high frequencies. How do you account for EMI in those designs?
Well, there's
go ahead.
Go ahead.
No, I was going to defer to you. I think you're Brian has been very helpful helping out many customers in PD applications, especially higher switching frequency. You're probably the most expert to answer these questions.
Well, yeah, there's a few questions, and yeah, I understand where you're coming from. You think, yeah, if you have a FET that's very high speed, FET switching, and you're running at high switching frequency, that's kind of asking for problems. But there's a few things really help. One of which is and this is something I didn't know until recently, that in a MOSFET, the parasitic diode can cause some ringing, some high frequency ringing. That parasitic element isn't present in the GaN FET, so it can't create some ringing. So that actually helps. Also, the GaN FETs are small, so placing them next to each other, and then real good layout, we have examples, really minimizes the ringing. So those two things really help a lot. And if you really need to, you can slow down GaN FETs. It's easy to do, to slow them down a little bit, but typically with good layout and the way they're constructed, you can have some good EMI performance.
For high, do you have a solution for high voltage designs?
High voltage meaning like a 650 volts and above. Today, we don't have a high, as a EPC today, we focus a lot of our efforts on mid voltage developments. For high voltage device, today we don't have the solutions for high voltage device. Right.
That's
but
true.
Right.
But
Sorry.
Josh is right. But many people have used the 200 volt, for example, FETs, and stacked them in series with multi-level to do solutions that way. And on the market, there is some high voltage GaN gate drivers. So there's papers like from APEC and other places that show that type of thing. We don't have an example board ourselves at this point.
Okay. If the gate signal is equal to 0, can the GaN FET still be on?
No. Well, in the diode mode, yes, I guess. Maybe it's a trick question, but maybe somebody's trying to get us, Josh. I don't know, but I agree with Josh. Yeah, no, it's not on in the forward direction.
In the future, can we use GaN for high voltage converters? Because we talk about GaN in automotive solutions, but for middle voltage, shall we use silicon carbide or silicon for high voltage?
There's other manufacturers out there of GaN FETs, though. Maybe that's not a good EPC question. I don't know. What do you think, Josh?
I can tell you that the way Alex usually answers that is
please.
that is that at 650 volts and below, that's really a GaN play. And once you get above that, you get more into silicon carbide.
Yeah.
So the 650 range is kind of like the middle, like the battleground for between GaN, silicon carbide, and silicon.
Right.
Okay. Any other questions? All right. I'll give it another second. And if not, we can wrap up. So I just want to say thank you to Josh and Brian today. And thank you for everyone for attending today's webinar. If you do have any other questions, please feel free to send them into the support links that Josh gave you. You will get an email within 24 to 48 hours with a link to view a recording of the webinar and also a copy of the slide deck. And lastly, just be sure to register for the remaining webinars in the GaN for Consumer Application Series, the next installment of which is next week. And Brian will be presenting, talking about GaN designs for power tools and vacuum cleaners and other kinds of, what else is on that list? other kinds of consumer devices.
Yeah.
All right. Thank you, everybody.
Thanks, everyone.
Have a great
Good to
day.
see you. You too.
Okay.
Bye.
Bye.
Bye.